Hi, welcome back. Today we're doing lesson 3 in unit 3 of our AP Calculus course. This lesson is all about the product and quotient rules. Unfortunately, unlike addition and subtraction, we cannot just simply split up a product or a quotient in derivatives. Instead, we have to apply these important rules. The product rule tells us that if I'm trying to take the derivative of some function f of x times another function g of x, then the resulting derivative is f prime of x times g of x plus f of x times g prime of x. In other words, you take the derivative of the first times the second plus the first times derivative of the second. And that can be extended to even products of 3 functions or more, where you take the derivative of one and leave the other two the same, and then take the derivative of the other, and so forth. But this is typically the size that we'll be dealing with. So remember, when you have the product of 2 functions, you take the derivative of the first times the second, plus the first times the derivative of the second. Let's try it. So notice that this is a product. This would not be that difficult for me to expand. I could certainly use expansion and multiply these two and then take the derivative using our basic rules. But let's practice our product rule. Derivative of the first. Okay. Remember, you just bring the exponent down 1 and the x goes away, and then 2 times 2 is 4, x to the first, times the second. Leave the second the same. Plus the first times derivative of the second. And there we have it. So one thing to note, I used a lot of parentheses around each part, and that's typically a very good idea. You can sometimes you'll be using parentheses that you don't need, but sometimes you absolutely have to use parentheses. There's never a time where using parentheses would tells you to get it wrong. So better safe than sorry. All right, practice 3.1. I would like you to find f prime of x. Notice that there is a product in there between the 2x and the cosine of x. Give it a try. Okay, so I'm going to use the product rule. Derivative of the first. So my first product I'm going to call 2x. So that's derivative of the first is 2 times the second is cosine of x. Plus the first, 2x, times derivative of the second, which is a negative sine x. All right, and then lastly, I take the derivative of that term there, and that's just going to be a minus 2 cosine x. All right, so you'll notice I didn't use quite as many parentheses this time, and I felt comfortable I was getting it right. And I could alternatively remove these parentheses here if I put the negative out in front. But I definitely need the parentheses when I put the negative there. So you realize it's not 2x minus, it's 2x times a negative sine x. And sometimes this 2 confuses people. They don't know what to do with it. Just remember, it just comes along for the ride. I went ahead and grouped it with the x and thought of 2x as my first f of x and cosine as my g of x. But you could also just say, okay, the 2 comes along for the ride on each term. And then think of it as x times cosine x. Both ways work. All right, next, let's talk about the quotient rule. The quotient rule is the derivative of the top times the bottom minus, there's a minus this time, the top times the bottom, it's derivative, all over the bottom squared. Now that's kind of a lot to memorize, but fortunately there's a nice little rhyme or whatever you would call it about this. So if we have a fraction, then I would say We have a high part and a low part, right? So the derivative of this fraction is low d high minus high d low all over low low. And so the way you remember that is that it's saying the low times derivative of the high minus the high times the derivative of the low all over low low, which is not exactly the order I wrote it in. It looks, I put d high times low, but that's just the way the rhyme goes. Low d high minus high d low all over low low. And some students occasionally will get these two terms mixed up, and they'll do like d low with high first, and then that gives you the wrong sign on your answer. So just be careful. Remember that just like I showed you with the product rule, we're going to take the derivative of the first things first. In the product rule, the first thing I had was derivative of f, because f's on the left. So I did derivative of the first times the second. With the quotient rule, I do derivative of the first times the bottom. The first being the one on top, right? So just remember that top goes first, left goes first. That being said, there are many people that traditionally write the product rule actually the other way, where because it's addition, I could actually start over here and say that it's first times derivative of the second. But I don't do that because then it doesn't match the quotient rule. I like it to match the quotient rule, and they're equally the same. So we're going to take derivatives of first things first, is how I remember that. And low d high minus high d low all over low low. All right, example 3.2. Let's find y prime. All right, we know that y prime is just abbreviation for dy dx, but we'll use it since they said so. So here we go. Low d high minus high d low all over low low. Low times low. There we go. Okay, your turn. I want you to find the derivative using the quotient rule, the product rule, and basic derivative rules. So see if you can do that. See if you can do practice 3.2 in 3 different ways and see if the results are equivalent. Now, just give it your best shot. I know you may not know all these different ways of doing it perfectly, but see if you can figure out how to use the quotient rule, the product rule, and basic derivative rules. Okay, so let's see what you did. Well, first, let's use our quotient rule. Well, actually, that's not true. First, let's rewrite this as x to the 1/4 power, right? There we go. Now, quotient rule says that f prime is equal to low d high. So what is that? 3x squared. So low d high minus high d low. So that would be a 1/4 x to the negative 3/4. Because you subtract 1 from 1/4. All over low low. Now, this is x to the 1/4 squared. And you could realize that that's actually going to be just 1/2, or you could write it like that if you really want to. So either way is okay. So that is the derivative using the quotient rule. Now, how would we do this with the product rule? Well, to do this with the product rule, I'd have to realize something, that this is really actually x cubed plus 2 times x to the negative 1/4. Then I can use the product rule. So I'm going to do the product rule in orange. So that'd be f prime of x. I'm going to take the derivative of the first, 3x squared, times the second, plus derivative, plus the first, x cubed plus 2 times derivative of the second. Not negative 4, negative 1/4. X to the negative, what is that? Negative 5/4? 1/4? When you subtract 1 from a fraction, you just take the denominator away from the numerator. So negative 1 minus 4 is negative 5. All right. Wow. That looks remarkably not at all the same, right? Uh, but, you know, maybe we could make this look the same because, and, normally it's okay to have different forms, but that's why I said they don't make sure that they're not, I didn't say look the same, I said equivalent. Well, we agree that this is x to the 1/2, right? I'm just going to make that little note right there. Well, if that's x to the 1/2, if I was to divide this into x to the 1/4, that would get me x to the negative 1/4. Do you agree? 1/4 minus 1/2 is a negative 1/4. Likewise, if I distributed into here, this negative with the 1/4 over here could make this plus a minus, and then x to the negative 3/4 minus 1/2 would give me a negative 5/4. So these are really the same. It's just that we've divided this x to the 1/2 into each one of these places. All right. So the last one I said was basic rules. Well, to do this with basic rules, I have to divide each term by x to the 1/4. So that would make this. Let me rewrite it over here. Another way of doing this would be x to the 3 minus 1/4 is, well, 3 is what? 12/4, so that would be 11/4 plus 2x to the negative 1/4. All right, so now we'll take the derivative, and that gives me 11/4 x. So 11 minus 4 is 7 to the 7/4 minus 1/2 x to the negative 5/4. All right, well, that is also looking quite different. And we could definitely make these equations look the same, doing some kind of factoring out. We'd have to distribute and then do some pretty interesting algebra factoring, but I don't want to go into that now because we're not studying algebra. We're studying calculus. So I'm going to cheat. And I'm going to type these equations in to Desmos. So here is, we've already pretty easily confirmed that the quotient and product rule were the same, but I typed in both equations. So here's the first one here. And I'm going to go ahead and turn on the rule we got with basic rules just to confirm, and you can see that they are, in fact, definitely the same equation. It is a little bit of an algebraic headache to make that happen, and we'll occasionally do some stuff like that, but I got some pretty nifty tricks that make it easy. I just don't want to go into it right now. So, moral of the story, they are the same. But when you take a derivative in a different way than someone else, be prepared to have your answer look nothing like theirs. And I'm sorry to say, it just gets worse as it goes on. When you get into Cal 2, 3, and then differential equations, I have often felt that the hardest part of doing differential equations assignment is confirming that your answer looks like the one in the back of the book, because are the answer key, because they can be completely different and they're both viable. And please, forgive your teacher when he takes a long time to grade calculus tests, because I can have 16 students get a question right and not a single one of those answers look the same. Okay, exaggeration, but you get the idea. So it can be pretty varied. Okay. Now, that being said, so there was lots of ways to do that one, and I guess what way would I typically do? I would probably actually do. I would probably do this. I think. I don't know. I'm not sure I would do the same thing every time. I would probably do that though. But here's a general rule. Okay, if the numerator of a quotient is constant, it is typically much easier to rewrite and use the power rule. Okay, that's going to be true a lot. So let's practice that. Let's find the derivative of 9 over 5x squared. Yes, I can do the quotient rule. But I find that when students use the quotient rule here, they mess it up because they're like low D high. They forget that the derivative of 9 is 0. So instead, I really want to see you rewrite. And in fact, I like to kind of think of that as 9/5 x to the negative 2 there. If you want to write it as 9x to the negative 2 over 5, that's fine, but just realize that over 5 just comes along for the ride, okay? So I like to make it look like that. I got a coefficient and a x with an exponent. Well, now it's cheesecake, right? Bring down the negative 2, and you have a negative 18 over 5, x to the negative 3. And we're done. So yeah, it's typically easier to rewrite and use the power rule. So that's my general rule there. This is my absolute steadfast, it is a terrible idea to do it otherwise. It is never a good idea. Never a good idea to use the quotient rule when the denominator is a constant. If you want to break your teacher's heart, turn in a quiz or a test where you used a quotient rule on something like this. I mean, yes, it can be done if you are very careful, but you will probably mess it up, and it is pointless. This is a constant. The quotient rule is for quotients of functions, not constants. You need to have x's on top and bottom to need the quotient rule. The derivative is simply 3x squared over 4 comes for a ride. Because you're pulling it out of the derivative as a constant multiple rule. So just no. Do not try and do something silly with that. Yeah, you could also, some people like to rewrite it as 1/4 x cubed. That's fine as well. But, for me, it's just, if I got a constant in the denominator, I just have that same constant in my answer. This is the way to do that, okay? Don't start over applying that stuff. All right, now that we know the quotient rule, it's time for us to find the derivatives of our 4 other trig functions. We already know cosine and sine, so let's do this. All right, the derivative of tangent x. I'm not going to go back to the limit definition. I don't have to because I can use the quotient rule. And as long as I get a quotient of things I know the derivative of, I got no problem. So the tangent is, of course, sine over cosine. So we know how this works, right? It's low d high minus high d low. Don't forget the negative of the derivative of a is always negative. All over low, low. And we could just write it cosine squared x like that. Okay, cosine x, and then I got minus sine x times the negative sine x. I don't want to rewrite this, so if you'll pardon me erasing a step and writing over it, I'm just going to take out that negative and make this a plus. So that makes this cosine. Oh, I did not give myself enough room, but I have a secret weapon. I can move this aside for a little while. Haha. Don't you wish you could do that on paper, right? All right, this is cosine squared x plus sine squared x all over cosine squared x. But what is cosine squared x plus sine squared x? That is 1. So this is 1 over cosine squared x, which is then equal to, what is 1 over cosine? Secant squared x. So the derivative of tangent is secant squared. All right. I'm going to move this. Oh, we'll put it here. There we go. There. Just in case. I don't know. It bothers me not to leave it there. Okay. Now, let's go down and let's find secant. I will be more judicious with my room taking here. Start over here. The derivative with respect to x of secant of x. Secant is 1 over cosine of x. All right, so typically it's a good idea to rewrite this as cosine to the negative 1, and then we could just use our rules like that. But I'd have to use a rule that you don't really know yet. We'll learn it in 2 lessons. So I'm going to have to use the quotient rule, even though I don't typically like to do that. So when I have a constant on top. But like I said, when you have a constant on top, sometimes it's easy to use the quotient rule. So it's not always. It just typically is. So let's do that. Low d high. So the derivative of 1 is 0. So that's just 0. Minus high d low. The derivative of cosine is negative sine. All over low low. All right. So that becomes 0 minus 1 times the negative sign. That is a 0 plus sine x. So this is sine x over cosine squared x. I'm going to write it as cosine x, cosine x. Actually, I could do it either way, but I want to match the way I usually write it for formulas. This puppy here is tangent of x. This is secant of x. So the answer is, for our derivative, is secant x tangent x. So the derivative of secant, secant tangent. All right, well then here we go. We have our formulas. The derivative of sine x, cosine x, tangent, secant squared, secant, secant tangent. These formulas over here you should already have memorized if you have memorized these, because they are basically the same, but they have a negative. So when you take the derivative tangent, you get secant squared. When you take the derivative cotangent, you get cosecant squared with a negative. Negative cosecant squared. Take the derivative of secant, you get secant tangent. Derivative of cosecant, you get negative cosecant cotangent. So you just put negatives and cos in there. This is the only one that's kind of weird, is the sine cosine, because they like relate to each other. All right, so would you please find the derivative of 3x squared tangent x? Pause the video and give it a try. All right, let's see how you did it. Let's see how you did. F prime of x, derivative of the first times the second, plus the first times derivative of the second. The derivative of tangent is secant squared. Okay, cool. Quick note, I don't know if I've talked about this very much, but I like, when I'm writing math, I really like to have parentheses around the arguments of my trig functions, because it makes it clear that this plus 3x squared secant x is not in the argument. But I force myself not to all the time, because it's important that you know about mathematic notation. Mathematicians will not put parentheses all the time for arguments. As a computer scientist, I find that obnoxious. It's a function. It should have parentheses. But, as a mathematician, I feel it. It's fine. Just remember that the argument will continue of tangent until there's a plus. So if I had like tangent x and then a y here, then that'd be saying the tangent of x times y, not the tangent of x and then y times whatever that is as a result. You would multiply xy first. All right. Okay, so that is our last practice problem of this lesson. I think the only thing that's left to do, is let's prove the product rule, and then I'll tell you what, we'll prove the product rule, and then let's go ahead and try and prove the quotient. So hopefully this is not too bad. So if you're not interested in why math works, then I guess you could just continue in your ignorant bliss. Stop the video and start working on your assignment. But for those of you that are interested in the beauty of mathematics, here we go. I need to say the derivative of f of x times g of x. Well, that is the limit as h goes to 0 of f of x plus h times g of x plus h minus f of x, g of x, all over h, right? Now, I'm going to do something a little bit clever. Well, not because I'm clever, but because somebody more clever than me told me to do this. But I'm going to do it nonetheless. So I have f of x plus h times g of x plus h minus, I'm going to do something kind of funny, and I'll explain what I'm doing. I'm going to do minus f of x times g of x plus h, and then I'm going to do plus f of x times g of x plus h, and then minus f of x, g of x, all over h. My college professor used to tell me that this is the oldest trick in the book, right? This is the oldest trick in the book, and that is adding 0. The second oldest trick is multiplying by 1. So I am adding 0. I do not want to change the value of this ratio here, but I do need to introduce some new things. So I know I need a minus f of x to go with that. So I know I'm going to do this for reasons that will be obvious in a second. But just agree with me that I did not change this because whatever I subtracted, I also added. So I really just added 0, which doesn't change anything. Now that I've done that, I'm going to just do some basic algebra here. I'm going to factor out g of x plus h. And that's going to give me f of x plus h minus f of x. Okay. Right. That's going to be there. All right. Then over here, I'm going to factor out f of x. So I factored it out. This was this group here, right? And then on this next group, I have an f of x in common, so I'm going to factor it out. So let me color coordinate here. There and there, right? So let's factor out f of x. So I have plus f of x times, no, I'll use these parentheses so you see what's, all right, so what's left over after I factor out f of x? Well, I got g of x plus h minus g of x. Okay, and then all over h. Oh, well, I don't like that orange down there. Come on. There we go. All over h. Cool. All right, next, what can I do now? Well, I've got a plus. I'm going to split this limit up. I got the limit as h goes to 0 of g of x plus h times f of x plus h minus f of x. And I can say this whole thing's over h, but I can just as easily say just that part is over h, because that's how fractions work, right? If I have 4 times 8 over 2, that's the same as 4 times 8 over 2, which is the same as 4 over 2 times 8. That's just how they work, right? Play around with that if you don't believe me. So I'm going to put it there because that's where that h should go when for what I'm trying to do. All right, plus the limit as h goes to 0 of f of x times. Now remember, I got to divide both terms by h, right? So I got to put an h over here as well. So I will put it on here because it looks most like what I want. All right, now I'm going to split this up even more. So I get the limit as h goes to 0 of g of x plus h times. Now we can't split derivatives over multiplication. We learned all that. We know that. We were talking about that all this lesson. But I can split limits up, which is kind of remarkable about limits. All right, and then over here I got plus the limit as h goes to 0 of f of x times the limit as h goes to 0 of g of x plus h minus g of x all over h. Well, what happens now? This is basically, it's basically over, y'all, because check it out. Let's take the limit of g of x plus h. That's not indeterminate. H goes to 0. It's just g of x. That's just g of x. But we know what this is, right? What's that? Well, that's f prime. All right, and then the limit as h goes to 0 of f of x. Well, actually, that's just a constant, really, because there's no h in that f of x. So it's just f of x. And then I know what this is. That is the derivative of g. And this was what we were trying to show. Derivative of the first times the second plus the first times derivative of the second. Are we ready to do the quotient rule? And I don't know if I have it copied over here, so let's do that. Okay, here we go. This is very similar to what I just did. Very similar. It's going to require us doing a little bit of magic, if you will. So here we go. We know what this is. This is the limit as h goes to 0 of f of x plus h over g of x plus h minus f of x over g of x all over h. That's what the derivative says that this is equal to, right? Okay, well, what to do now? Well, I am actually going to just get rid of my stacked fractions. I mean, when we practiced taking the limits, we knew that when we saw these stacked fractions, we just need to simplify them. And so that's a good place to start, right? Let's do that. And what does that give me? Well, that gives me the limit as h goes to 0 of f of x plus h times g of x. Because when I multiply that here, the g of x plus h and this g of x plus h will cancel. So I have f of x plus h times g of x, right? Now, over here, when I multiply here, it's the g of x's that will cancel. And I'll have f of x times g of x plus h. Oh, wait, hold on. I don't want to have those slashes there. That bothered me. Okay, I'll rewrite f of x times g of x plus h. Okay, now on the bottom, we have h times g of x plus h times g of x. All right, not too shabby. This is actually not too far from what we need. But for example, this f of x plus h, if I just had an f of x here alone, I could do it. So I'm going to do something clever. Again, not so much because I'm clever, but because someone else told me to do this. But at some point, someone, perhaps Isaac Newton or Gottfried Leibniz, was very clever, and they suggested doing this, right? And with enough time and effort, maybe we could figure it out too. But I already know the answer, so I'm going to do it. So I'm going to add and subtract f of x times g of x. Okay, and I'm going to do this because it gets me what I need, and it will make sense. All right. I think I've got that correct. I'm starting to get a little bit blinded by all the letters. Okay. Let's factor. Let's see, what can we factor? Well, let's see here. I can factor out of this first group here. Remember, I didn't change anything because I did a negative f of x plus g times g of x and then a positive f of x times g of x. So what can I factor out there? Well, I can factor out a g of x, right? So this is the limit as h goes to 0 of g of x times f of x plus h minus f of x, which is exactly what I'm trying to find, right? I want that, right? Plus, over here, I'm actually going to do something kind of funny. I'm going to factor out a negative f of x, okay? Because I really want this in front. I want to, if you don't mind me doing two steps at once, I'm going to rearrange this. So I'm going to pull out a negative f of x, and so that makes this when I factor out a negative f of x, that's going to make this a positive g of x plus h, which I will put in front. And then that makes that a negative g of x. So I'm just factoring out a negative, which makes this negative and that positive, and then putting the positive term in front. All right, and then this is all over h times g of x plus h times g of x. I don't know why I have that rogue parenthesis there. I don't need that. I'll get rid of it. Okay, so how does this help us? Well, actually, believe it or not, this is pretty close to done. Because I can now divide each term by h. And I'm going to do so like this. G of x is a constant, so that's going to come out in front. But you know what? Let's take two steps, because this is actually a little bit weird. So I'm going to divide, and I get to pick. When I divide this term, I can do that factor on the left or this factor. Well, I'm going to do this one because that's the one I want it, right? I want this one. I want that one over h. And then here I got f of x, right? And then I'll divide this one by h. Got to pick one of them to divide by h. Let's do this one. Okay, and then that's all over what? Well, yes, that's right. I still have a denominator because I only divided by the h. So it's all over g of x plus h times g of x. All right, now I can do a whole bunch of limit properties, but I think we've pretty much got this. First of all, this is a constant because, yeah, it's got x in it, but as far as h goes, it's a constant. It's got no h in it. So I can pull that out of the limit when I put the limit to this first little area over here. So when I take the limit as h goes to 0 here, do you agree that that's just going to be g of x times f prime of x? Because that as h goes to 0 is f prime. And then over here, that f of x has no h in it. So that's just going to be f of x. And that must be g prime of x, right? Now on the bottom, when I take the limit as h goes to 0 here, then this g of x plus h is just g of x. And now it's g of x times g of x, which is low, low. So it's low d high minus high d low all over low, low, which was to be shown. And that is the derivative. Okay, now that we've got the quotient rule proved, we can now prove that our power rule works for negative exponents. If you recall, we only proved that the derivative with respect to x of x to the n is equal to n times x to the n minus 1. We have only shown that that is true when x is a positive integer. And we also showed that it's true when n is 0, since, you know, that would make it a constant. We could prove we proved the constant rule. So we now know that that's true for all positive integers. I want to show that it must also be true if the exponent is negative. You know, so if it's x to the negative 4, then the derivative is negative 4x to the negative 5th. So I have just a little setup for us here. Let's suppose that n is an element of z plus, meaning the n is a positive integer. Then negative n must be a negative integer, right? Okay, so with that in mind, let's take the derivative with respect to x of x to the negative n. Well, that is equal to dx of 1 over x to the n. For that, I can use the quotient rule, right? So the quotient rule says low d high, what's the derivative of 1? Well, that's 0. Minus high d low. Well, that's n times x to the n minus 1. All over low, low. All right, well, that thing times 0, that's kind of pointless, right? So then it's negative n times x to the n minus 1. And power raised to a higher power, we multiply, so this is x to the 2n, right? So we're pretty much almost done, except for the fact that I need to reduce these fractions, right? I've got n minus 1 and 2n. So let's subtract n minus 1 minus 2n. So n minus 1, I'm going to do just a little bit of scratch work here. N minus 1 minus 2n. Because remember, when you have the same base and you want to simplify it, division, you subtract the exponents. So this is equal to a negative n minus 1, right? So this is negative n times x to the negative n minus 1. So look what we've shown, though. We've shown that the derivative with respect to x of x to some negative power must be equal to negative n times x to the negative n minus 1, which is exactly the same. So for example, if we have x to the negative 4, then my n is 4, right? And so it would be a negative 4x to the negative 4 minus 1 is negative 5. Or in other words, bring this puppy down and subtract 1. And that's it. So we've proved quite a bit today. And now in the next lesson, we'll put the stuff to work.